The OrongoDB DGL adapter helps developers export their OrongoDB graphs into Deep Graph Library, a Python package for graph neural networks. With the help of the adapter's notebook guide, this Lunch and Learn will cover DGL basics, OrongoDB to DGL usage, DGL to OrongoDB usage, as well as unique cases. Timestamps are made available in the description should you wish to fast forward. Thanks for joining us, and let's get started. DGL was built for easy implementation of graph neural network models on top of existing deep learning frameworks such as PyTorch, MXNet, and TensorFlow. It offers a versatile control of message passing, speed optimization via auto-batching and highly tuned sparse matrix kernels, as well as multi-GPU-CPU training to scale to graphs of hundreds of millions of nodes and edges. DGL represents a directed graph as a DGL graph object. You can construct a graph by specifying the list of source and destination nodes. Nodes in the graph have consecutive IDs starting from 0. The following snippet constructs a directed star graph with 6 nodes and 5 edges. A heterogeneous graph is specified via relations. Each relation is a string triplet containing the source node type, the edge type, and the destination node type. For example, we have users follow user. Since relations disambiguate the edge types, DGL calls these canonical edge types, as we can see through this attribute here. The following snippet constructs a heterogeneous graph with 7 nodes and 7 edges. Graphs will often contain attributes on its nodes and edges. Although the types of nodes and edge attributes can often be arbitrary in the real world, DGL graphs only accept attributes stored in tensors, which means of numerical content. Consequently, an attribute must have the same shape across all the nodes or edges it belongs to. In the context of deep learning, those attributes are often called features. You can assign and retrieve node and edge features via the NData and the eData interface. In this example, we use our heterogeneous graph from above to assign the age attribute to the user nodes and the hours played attribute to the plays edge relationship. Let's run the snippet. So keep in mind once again that due to the fact that DGL features do not accept non-numerical content, the following line would not work. This concludes the basics of DGL. You can refer to docs.dgl.ai for further documentation. Let's move on. I've created my adapter using the Python Orongo database client, which points to a temporary cloud endpoint generated by the OrongoDB Cloud Connector package. Now that we have this ADB DGL adapter object, let's take a look at OrongoDB to DGL functionality. OrongoDB to DGL usage provides 3 functionalities: transition by graph name, by collection names, and by metagraph. In this first example, we take a look at OrongoDB to DGL by graph name. It's as simple as specifying the existing graph name in OrongoDB that you'd like to convert to DGL. In the example that I've shown above, we've imported some dataset regarding fraud detection relationships to our OrongoDB endpoint for example purposes. The data here is arbitrary, so let's just assume that it's some random data specifying relationships between customers, accounts, and banks. For now, let's go back to the API and run the snippet. As we can see, we've created our DGL graph using the fraud detection graph from OrongoDB. An alternative is to specify the list of vertex and edge collections to convert into DGL. We can run this snippet below to convert the account, class, customer vertex collections, along with the account holder, relationship, and transaction edge collections into a DGL graph. Recall that DGL only accepts node and edge attributes of numerical content. OrongoDB does not have this restriction, so if you'd like to bring over your attributes over to DGL, you can rely on the OrongoDB to DGL via metagraph solution. Note that the first 2 solutions we've shown above do not bring over node and edge attributes, as to avoid the risk of encountering non-numerical content. With this metagraph approach, though, we let the user specify which node and edge attributes can be safely brought over to DGL given their numerical nature. In this example, I am bringing over 3 node attributes from the account vertex collection and 3 edge attributes from the transaction edge collection, along with some other numerical-based attributes. Once we run the snippet, we can access these attributes via the NData and the eData interface to see that our attributes of numerical content have been safely brought over. This concludes the basics of OrangoDB to DGL usage. If you're interested in learning how you can bring over non-numerical content attributes from OrangoDB to DGL, fast forward to the unique cases timestamp. Moving on though, let's take a look now at DGL to OrangoDB. This first example uses DGL's built-in Karate Club dataset, a homogeneous graph capturing 34 students, documenting links between pairs of members who interacted outside of the club. Note that when there is only one relation defined in a DGL graph, the canonical edge types default to _n for nodes and _e for edges, as seen in the output below. As far as the API, we can just uncomment this snippet here and specify the Karate graph as the OrangoDB graph name we'd like to have, along with the DGL graph object to convert to OrangoDB. From here, we can see that we've successfully converted our graph. So if I head over to the Karate graph page and load the full graph, I can see now that indeed the Karate Club dataset has been successfully imported. I can also take a look at the edge collections along with the node collections. Continuing our DGL to OrangoDB functionality, we use our previously shown social graph example to demonstrate the adapter's ability to easily convert heterographs to OrangoDB. In this case, the DGL graph has two node types, user and game, and also has three edge types, follows, likes, and plays. As a result, the created OrangoDB graph will of course have two vertex collections and three edge collections, along with their numerical attributes properly transferred over. Before we run the snippet, let's just once again go over the canonical edge types and notice the difference between the previous example and this example now. Note how there is no default _n and _e node and edge type. With that being said, let's uncomment the DGL to OrangoDB snippet, provide the graph name for OrangoDB to use along with the DGL graph object, and run the snippet once again. We can see here that the social graph has been created, and if we head over to our web interface, we can see that we can load the full graph. Here it is, and we can now also access each and every vertex and edge collection specified within the DGL heterograph. This concludes the basics of DGL to OrangoDB usage. If you're interested in learning on how you can convert DGL's numerical attributes into non-numerical content for OrangoDB graphs, fast forward to the unique cases timestamp. You may have OrangoDB attributes of non-numeric types that you'd like to bring over into your DGL graph. This is possible through a user-defined ADB DGL controller, which we'll use to override the ADB attribute to DGL feature method. Let's use the previously defined metagraph as our example, modified to include some string-based, non-numerical attributes. Overriding the ADB attribute to DGL feature, controller method provides users the ability to specify how their OrangoDB attributes can be converted into DGL features in a case-by-case basis. Let's say a user wants to preserve the name attribute of the class vertex collection, which looks like this. A solution here would be to map all the name values to incrementing numbers such that this information can be stored in a DGL tensor. I previously mentioned that overriding this method provides the user the ability to establish case-by-case behavior, and we'll do exactly that using the following three parameters at our disposal. We have the attribute key name, the collection that the attribute belongs to, and the actual value of the attribute for a given arbitrary document. We'll first start by checking that the collection we're currently on is in fact the class collection. Then we'll check if the attribute key that we're on is the name attribute. And from here, we can create a custom dictionary to map all possible class names to incrementing numbers. Following that, we can simply call the get function for a given Python dictionary fetch the value associated to the class name, and return -1 if that value is not found within this dictionary. From here, we've defined custom behavior for our ArongoDB DGL controller. Let's pause here to take a look, and I'll cut to a fully completed ADB DGL controller. Given the metagraph specified above, this is what the final representation of our custom controller looks like. We still have our class name logic down here. We've just added extra steps to deal with non-numerical attributes belonging to the customer document collection and non-numerical attributes belonging to the transaction edge collection. We also invoke super here as a good practice to deal with any unchecked case. This basically calls the ADB attribute to DGL feature method of the built-in default controller, such that any case here that hasn't been checked is dealt with the parent controller. Also, for good practice, we wrap all of this in a try except and return 0 on the following exceptions. We can create a new adapter, providing the custom ADB DGL controller as the second parameter in the constructor, right after the regular database instance we set up previously. And we can just call the ArongoDB to DGL method just like we did normally, providing the graph name and the ArongoDB metagraph. Once it's created, we can access, for example, some general graph information, just like the number of edges and the number of nodes. But more specifically, let's take a look at the NData interface, for example. We can see that the attribute name belonging to the class node type did in fact properly convert. So we can see here, this was, from what I remember, bank, branch, account, and customer. Here are some other examples, so I'll pause here for you to take a look. But at the end result, we have successfully transferred the following non-numerical attributes into DGL using a custom user-defined ArongoDB DGL controller. Let's move on to the other unique case. You may have DGL features that you'd like to store in ArongoDB in non-numerical format. This is possible through another user-defined ADB DGL controller, which we'll use to override the DGL feature to ADB attribute method. For this example, we'll use one of DGL's built-in mini graphs, the click graph. Notice once again that we've inserted node and edge data that we set up for example purposes. So, just like we created a custom controller for ArongoDB to DGL, note how you can do the same for DGL to ArongoDB purposes. Imagine a situation where a user seeking to convert the click graph into ArongoDB does not want to store these attributes in numerical format. This would require overriding the DGL feature to ADB attribute, which provides the users the ability to specify how their DGL attributes or their DGL features should be converted into ArongoDB attributes. Once again, this is done on a case-by-case basis, similar to our previous custom controller behavior. The user has access to the DGL feature key name, the collection of the soon-to-be ArongoDB document that hosts this attribute, as well as the actual value of the DGL feature. So from here, let's remind ourselves that given the fact that the DGL click graph only has one relation, its canonical types will be of default type. So that's why you'll see often the _n and the _e for this graph's n type and e type. Recall the previous snippets that we've shown above. This means that I don't have to do a collection check because essentially there is only one collection for nodes and one collection for edges. So I can go ahead and check the attribute name straight away. So I want to, let's say, convert the click n data into string-based values. I can start by playing it safe and wrapping my logic around a try except. And now I can paste this snippet in my try clause that provides a quick mapping of numbers 1 to 6 string-based German numbers from 1 to 6 once again. So this is the custom behavior that we want to achieve for this given DGL feature. I'll pause here and I'm going to cut to the fully completed controller so that you can get a better idea of what this looks like. This is the final representation of our custom ADB DGL controller. We can see that our click end data handler is still there. We've just added an extra step to handle the click edge data DGL features. We turn them here in this case into Boolean values. And we also invoke super as a good practice to make sure that any case uncovered by these handlers is properly dealt with via the parent DGL controller. Just like in our last custom controller example, we have to recreate the adapter and specify the new controller in the constructor. Following that, we can invoke the DGL to ArongoDB method from the new custom adapter, specifying the graph name along with the DGL graph object. We can see that the adapter has successfully created the graph, so let's head over to our web interface and load the click graph within ArongoDB. We can indeed see that this is the DGL graph, and to double check that the attributes have been properly transferred over, we can see that the DGL numerical features for the edge attributes have been transferred over now to Boolean format, just like we specified in our controller. We can also see that the node data has been successfully transferred over from numbers of 1 to 6 now to strings representing the numbers of 1 to 6 now in German. Note again that overriding this controller method is only required if you don't want to keep the numerical-based values of your DGL features in ArongoDB. This concludes the ArongoDB DGL Adapter Lunch and Learn session. I've left some links in the YouTube description should you be interested to learn more about the adapter. Once again, thank you for joining us and feel free to reach out for any feedback or inquiries. All the best.